Hello, my name is Jonathan Castillo, and this is my Case Connection Unit 4 video assignment and script. I chose to answer Case 2 and Case 3. I'll go over Case 2 first. So Case 2, Scenario 1. It's very likely that the patient has a deficiency of the mitochondrial branched chain alpha keto acid dehydrogenase complex. Screening test was positive for branched chain amino acids, which means that there is a defect in the catabolism of leucine, valine, isoleucine. This is occurring at the oxidative decarboxylation step of the catabolism via the mitochondrial branched chain alpha keto acid dehydrogenase complex, or the BCKAD complex. Even though the patient's family shows no history of genetic diseases, the patient likely has maple syrup urine disease, which is an autosomal recessive disease that causes genetic defects. Since it is recessive, this would explain why it has not shown up in other family members. Leucine, isoleucine, and valine are already essential amino acids. Prior to the deficiency of the BCKAD complex, human beings cannot synthesize these from metabolic intermediates and must obtain them through diet. But it should be noted that these may have also formed via aminotransferases through a reversible reaction. This means that the transferases are reversibly interconverting all three amino acids from their alpha keto acids that are already formed. The primary potential vitamin that could be used to help a MSUD condition would be thiamine. Thiamine helps with the subunit E1 of the BCKAD complex because it is thiamine dependent. This is because when thiamine is present, the E1 subunit can decarboxylate the alpha keto acids. But by taking thiamine supplements, the BCKAD complex will be able to function again and convert the alpha keto acids, and catabolism can occur. Scenario 2. Based on the examination and medical history of the patient, this is likely a homogeneous oxidase deficiency. This enzyme is primarily used in tyrosine metabolism, converting tyrosine to amino acid, glutamate, acetyl-CoA, and acetate. This first involves the transamination of tyrosine, and after several reactions, homogeneous acid is formed. This homogeneous is converted to malonyl acetoacetate via homogeneous oxygenase, which is where the deficiency can occur. Buildup will convert to alkaptin, leading to alkaptonuria. Buildup leads to darkened urine, connective tissue pigmentation, joint and spine arthritis, along with the cardiac valve destruction. This would explain the patient's back joint pain, pigmentation of ear, and the aortic stenosis. In homogeneous oxidase deficiency, there is no amino acid that becomes essential, but phenylalanine is already an essential amino acid converted into tyrosine. In this case, tyrosine is a non-essential amino acid, which can be synthesized by humans without having to obtain through diet. It should be noted that tyrosine can also be consumed in the diet, but it is primarily synthesized from the essential amino acid phenylalanine. So long as there's phenylalanine available, tyrosine metabolism can occur. Though there is no medication that can cure alkaptonuria, there are several treatments that can help with the condition. Vitamin C supplements may reduce the conversion of homogeneous state to benzoquinone acetate, which is responsible for the dark urine color. Nitisinone can also be used, which inhibits the enzyme 4-hydroxyphenylpyruvate deoxygenase, which would also help with reducing the levels of homogeneous buildup. Scenario 3. Based on the patient's condition, this is likely a phenylalanine hydroxylase enzyme deficiency, or also tetrahydrobiopterin BH4 deficiency. The specific amino acid that is no longer being metabolized is phenylalanine. Phenylalanine metabolism primarily is used to convert phenylalanine into tyrosine through a hydroxylation reaction involving BH4 and phenylalanine hydroxylase. If either are deficient, then tyrosine will not be converted, and phenylalanine will accumulate, causing phenylketonuria, or PKU. This will explain the higher than regular levels of phenylalanine from the newborn screening test. Normally, without a deficiency in phenylalanine hydroxylase, or BH4, phenylalanine is an essential amino acid. But in a condition like phenylketonuria, tyrosine will become an essential amino acid. It's therefore important for people with phenylketonuria to take tyrosine supplements. This will help with the last step of the phenylalanine metabolism by essentially bypassing phenylalanine metabolism altogether. But even taking tyrosine supplements will not be enough. For patients with phenylketonuria, should also take in foods free of phenylalanine. This will help with the first step of phenylalanine metabolism, as less phenylalanine will prevent accumulation. For patients the same age as the infant in the scenario, formula that lacks phenylalanine will still provide protein and energy for growth. It is crucial for such dietary restrictions to start early in a patient's life, as reducing phenylalanine levels will prevent neurological and psychological changes. Case number 3. So, gout forms mainly due to purine degradation of adenosine and guanosine. After several reactions, xanthine is synthesized and it will then be converted to uric acid via xanthine oxidase. An increase in uric acid production leads to hyperuricemia, causing gout on the joints because uric acid is insoluble. Temperature lowers solubility, leading to crystal formation specifically on joints. But based on this patient's condition, the gout may have formed due to a defect involving overproduction of purines, decreased salvage of purines, or being unable to excrete the uric acid in urine. So normally purine synthesis would begin with ribose 5-phosphate formed from the pentose phosphate pathway, or PPP. This is converted into the active 5-carbon sugar phosphoribosyl pyrophosphate, or PRPP, via the phosphoribosyl pyrophosphate synthase. This PRPP goes through several reactions to eventually form inosine monophosphate, or IMP, which then leads to the formation of adenosine monophosphate, or AMP, and guanosine monophosphate, GMP. Overproduction of these purines usually occurs due to a deficiency in the enzyme involved in purine metabolism. An example of overproduction of purines would be glycogen storage disease type 1, also known as von Gurk disease, in which glucose 6-phosphatase or the transporter enzyme glucose 6-phosphate translocase is deficient. Ribose 5-phosphate sugar builds up that would eventually be used for to overproduce purines, uric acid, and ultimately gout. Common side effects of a condition involving overproduction of purines would include hypoglycemia, lactic acidosis, and hyperuricemia. In some cases, there is even the presence of an enlarged liver, along with a protruding abdomen. In comparison, the patient does have hyperuricemia based on the serum test showing above the normal uric acid levels, but this would not explain the lower than normal uric acid in the urine test. There is no indication of an enlarged urine or protruding abdomen, only his foot is in pain. It is unknown if the patient has lactic acidosis, hypoglycemia, or any of the other conditions associated. Tests would need to be done to determine if the patient has any other unknown conditions. A liver biopsy or molecular genetic test could also be done. Based on the patient's condition, the overproduction of purines would not be the best explanation for the presentation of the specific case of gout. Another possible explanation for the presentation of the specific case of gout could be decreased salvage of purines. Salvage is another form of purine synthesis that turns purine bases into monophosphate nucleotides of the purines. Enzymes involved are adenine phosphoribosyltransferase, or APRT, and hypoxanthine guanine phosphoribosyltransferase, or HGPRT. So a deficiency of in these enzymes would decrease purine salvage. An example of a decreased salvage condition would be Lesch-Nyhan syndrome, in which the HGPRT enzyme is inhibited and bases would accumulate, contributing to uric acid overproduction. Side effects of decreased salvage condition like Lesch-Nyhan syndrome would include hyperuricemia, abnormal uric acid values would also be present, and most people with Lesch-Nyhan syndrome also had self-injurious behavior like biting lips and headbanging. In comparison, hyperuricemia would explain why the patient's uric acid levels were higher than normal, causing gout. This condition would also explain the lower than normal uric acid in the urine test, but the patient had no evidence of self-inflicted injury or trauma other than the gout. So a genetic test would help to determine if a deficiency in a salvage enzyme. Further observation of the patient could also be done to see if any self-inflicted injury occurs. More information is needed, but it does not seem that the patient has gout due to a decrease in purine salvage. Thus, likely the best explanation for the specific presentation of gout is decreased urinary excretion of uric acid. An example of how this condition can occur is through excessive alcohol consumption. The ethanol in alcohol increases ATP degradation to uric acid precursors. This increases purine nucleotide degradation by enhancing the turnover of adenine nucleotides, which can then be used for excess uric acid synthesis. But at the same time, alcohol also impairs renal urate excretion because it increases lactic acid production, leading to lactic acidosis, creating competition for urinary excretion between lactic acid and uric acid. The side effects of the condition that causes decreased urinary excretion of uric acid is the closest to patient's condition. The patient does have hyperuricemia based on the high uric acid levels in blood tests, but the patient also has low uric acid levels based on the urine test results, which is like decreased urinary excretion of the uric acid conditions. But this patient does not drink alcohol and instead drinks soda. This would still cause a decreased urinary excretion because soda contains high levels of fructose. So switching over from diet soda to regular soda would mean that the patient is ingesting large amounts of fructose and or high fructose corn syrup. In fructose metabolism, fructose 1-phosphate is normally broken down by aldolase B, but when there is high fructose present, aldolase enzyme activity decreases. Fructose 1-phosphate levels increase, and intracellular phosphate decreases, meaning less ATP is produced while AMP production increases. AMP then can be converted to IMP to be then used for uric acid production. What would likely occur through the continual ingestion of large amounts of fructose is insulin resistance, which is what causes the decreased excretion of uric acid. Though it is likely that the patient has type 2 diabetes, a blood glucose level test should be done to determine if the patient is diabetic. Overall, decreased urinary excretion of uric acid is the best explanation for the patient's condition. And here are my references. They're all provided at the end of the script that I will be uploading. And that is it. Thank you all.